Hello everyone, in this video I'm going to be talking about Friedel-Craft alkylations and acylation reactions. I'm going to begin with talking about Friedel-Craft alkylation, and eventually I'll talk about its drawbacks, and I'll eventually talk about Friedel-Craft acylation, how that's more beneficial sometimes compared to Friedel-Craft alkylation. And eventually generally I'll talk about what compounds cannot do Friedel-Craft alkylations and acylations. So to start out with, we'll create an electrophile that's going to be a possible carbocation. Sometimes we don't really create a carbocation, especially if it's in a primary. But then the drawback is if you're creating a carbocation or if you are on the verge of creating a carbocation, the rearrangements could take place and you may not get the product that you really want. You use some Lewis acids such as AlCl3 or FeBr3 as your catalyst, just like you use in case of bromination and chlorination of aromatics to make these electrophiles even more electrophilic. So to start out with, I have this simple example where the benzene is combining with this methyl chloride in the presence of an AlCl3. If I want to go ahead and create my electrophile, so do this first step with this AlCl3. So the lone pair on this chlorine is going to attack the aluminum, and that's like an acid-base reaction. I'm just going to go ahead and write down CH3 here, and have chlorine with two lone pairs left, and have Al with an extra bond. As a result, Al gets a negative charge, this chlorine gets a positive charge. Once this chlorine gets a positive charge, it makes this carbon even more electrophilic because chlorine is more electronegative and now it had a positive charge on it. So that makes this benzene ring pi bond attack this carbon even more successful in this particular case. So the next step would have been, okay, I'll take this benzene and I'll take this electrophile they have created. So I don't really want to break this bond because if I do so, I will get a positive charge on this carbon and that would make it a primary carbocation or even like a methyl carbocation, and that's going to be very unstable. So you don't want to do that. So I'll go ahead and use this pi bond and attack on this carbon, and then that actually ultimately breaks this carbon-chlorine bonds, and that will satisfy the charge on this positive charge on the chlorine. If you were about to make a secondary or a tertiary carbocation, you could technically break that carbon-chlorine bonds to make a more stable carbocation. If it's making in a primary carbocation, you don't really technically break the bond. You just leave it as it is and have the pi bond of your benzene ring attacking that carbon. Now, I can have, let's call this 1, call this 2 because this benzene is symmetrical. So I can have this 1 or 2 attached with the methyl group. It doesn't really matter. So if I have a methyl group on this second carbon, then your carbon 1 is going to become electron deficient. So there was already hydrogens there. So keep that in mind as well. And then you can draw a bunch of resonances. So this comes down here. So when this comes down here, let's see how that's going to look like. Double bond there, positive charge there. And then I can have another one. This moves down here, and this moves down here. You get a double bond here, positive charge here. And then eventually I can have the AlCl4 minus grabbing this hydrogen here, and it's restoring the aromaticity. I'll put it right here. Let's go ahead and erase part of it. I'm going to take away that hydrogen as well. So you go ahead and recreate this bond and restoring the aromaticity. in that particular case, and then your side product is going to be HCl. So like I said, if you are about to make a secondary carbocation, then you can go ahead and break the bond when you uh, making the electrophile. Like for example, suppose I had this secondary alkyl halide with AlCl3. So I can go ahead and do this first step where the lone pair on the chlorine attacks the aluminum. And now I have Cl there with a positive charge, and then I got AlCl3 with a negative charge. And now I can actually go ahead and break this carbon-chlorine bond, because when you do so, you create a more stable carbocation, which is going to be the secondary carbocation. But I wasn't really able to do that before because it would make a primary or a methyl carbocation. So you don't really do that when you're making a primary or methyl carbocation, but if you're making a secondary or tertiary carbocation, you can go ahead and break the bond and make the carbocation and have that carbocation attacked by the pi electrons of benzene ring, and the rest of the mechanism is going to be very similar. What if you have something like this? So this is where the drawbacks comes in. If I take this example, I would expect I'm going to go ahead and get this product. So 1, 2, 3 carbons. So keep track of your carbons. 1, 2, 3. 1, 2, 3. But instead, I'm not really going to get that, but your major product is rather going to be this guy. So that would be your major product. And why that really works, I'm just going to show you the mechanism for the electrophile creation. The rest of the mechanism is going to be the same. That's because you can have a carbocation rearrangements whenever you have a possibility of creating a better carbocation. So suppose in the first step, I'll have this lone pair on the aluminum, chlorine attacking the aluminum, and then I'll just go ahead and copy this down here. I'll have AlCl3 there with a negative charge here and a positive charge here. So now I know I don't want to break this carbon-chlorine bond, because if I do so, I'll get a positive charge on this carbon, and that makes it a primary carbocation. So instead, what I could possibly do is a hydride shift, because the hydrogen on here, I can have this move down here, and when this moves down here, this comes out. So this is going to be a 1,2 hydride shift. And in doing so, I get the positive charge at the second carbon instead now, and you're going to have AlCl4 minus, obviously. So then you will have this as your electrophile, and when this carbon, the benzene attacks that particular carbon, or the second carbon, you make the isopropylbenzene as your final product instead of propylbenzene. So that's going to be the drawback of doing these Friedel-Craft alkylation. These Friedel-Craft alkylation works really well if you're trying to create like something, if you're using tertiary alkyl halide, or even a secondary alkyl halide, or even like a methyl halide or ethyl halide, because in those cases you don't have any possibilities of rearrangements. But in some cases, if you use like propyl chloride or propyl bromide, you can have the rearrangements. So what's the remedy in that? The remedy is do Friedel-Craft acylation instead, and then maybe reduce it a little bit, and reduce it to an alkane later on. So when you go ahead and do this reaction instead, you end up making this as your product, because this will not do any carbocation rearrangements, and I'll show you the mechanism in a minute. And then you can go ahead and actually get rid of that carbonyl and make this product right there. And how would I do that? I can do either zinc mercury with HCl, or I can use hydrazine, which is N2H4, where you may see this written H2 and H2 with KOH. So this first one is called an Clemson's reduction, and the second one is called Wolff-Kirchner's reduction. So both of those works fine. One of them is under acidic conditions, the other one under basic conditions. One of the other differences, this Clemson's only reduces the benzylic carbonyl to an alkane, but the hydrazine or the Wolff-Kirchner can reduce not only the benzylic carbonyl, but the other carbonyls that's going to be on the chain outside the ring. So you can do this way, and um, how the mechanism is really going to work. So let's talk about how the electrophile is going to be created. So I go ahead and use this right there. And I know I got 3 lone pairs there, and I have AlCl3. So I can go ahead and do this nucleophilic attack, and then I'll have, let's go ahead and take this away. And I'll have AlCl3 with a negative charge here, positive charge on the chlorine. So here I can actually go ahead and have this lone pair of carbon on the oxygen go back to create a triple bond, and this will go ahead and knock out the carbon chlorine bond, making AlCl4 minus that you will use later on, and then also making um, this psyllium ion with oxygen having a positive charge here. This obviously have a resonance where I can have this coming down here, and if I draw it this way, it will have a positive charge on the carbon. But between those two, the first one is the more stable resonance structure, because in the first one you have every atom with an octet completed. But in either case, when you draw the second resonance, this carbonyl carbon is the one that gets a positive charge, and as a result, it gets attacked by the benzene rings. So the rest of the mechanism is more or less is going to be very similar to what we have seen so far. So I can go ahead and take this. So now I would have this right there with a positive charge on here. Then you can draw the resonances, the resonance structures. When you draw the resonances, I'm just going to go ahead and do this quickly right here. You get a double bond here, positive charge here, and this comes down here. This gets right here, and then eventually I can go ahead and use AlCl4 minus to grab this proton and this restored electron density back. So that's how you can do it, and eventually you can do reductions where you can convert them to a straight chain alkene. If you have a carbonyl group on it, then it's going to be a meta director. It's going to be useful in doing next substitutions on the benzene ring. But if you have just an R group, an alkyl group like you have in this reaction, in this product here, then it's going to be an orthopara director. What are some limitations we have on this Friedel-Crafts that Friedel-Crafts cannot really work if you have a nitro group on it, or CF3 or NH3? And even like how now you probably wonder how you really get an NH3 plus group. But technically, even if you have any amine group, it will not work. That's because when you add in loose acid, as soon as you add in a loose acid, it will protonate that nitrogen and it becomes positively charged, and as a result, it will not do Friedel-Crafts alkylation or even an acylation. So this is the limitation for Friedel-Crafts alkylation and acylations that it does not work if you have a strong electron withdrawing group, and even if you have an amine groups, whether it's an NH2 or NR2, it will not do Friedel-Crafts alkylations. Let's do this example before we go. So I had this bromine here and bromine here, and then we got the methyl propylene group here, and I got to worry about how I take care of put those two together right next to one another. There's different ways you can do these things, but sometimes you gotta really be careful with how you're gonna be putting the things, putting the substituents so that it directs the next substituents at the particular location you really want to. If I'm doing this reaction, I would go ahead and I can go ahead and install, do the acylation first, because when I do this acylation, I'll get this, and then I can go ahead and reduce this by using zinc and mercury in the presence of HCl. So that's just going to be your Clemson's reduction. Now you got this propyl group on it. And then after getting a propyl group, if I use a Br2 right now, if I do bromination, it will go on the para position, but I really want this on to be the ortho position. So maybe I can block the para position by doing H2SO4 with SO3, so fumic sulfuric acid. And now I can go ahead and do the bromination. So I can do Br2 with FeBr3. So remember, I got two groups now, but I'm going to listen to my electron donating group because that's going to be activating the ring. So that's going to put the bromine ortho with respect to the propyl group. That's because your para position is already taken, and then I can go ahead and get rid of this by using water and acid and heating it. So when you do so, you can unblock this sulfonic group that you have posted there. So this is how it's gonna look like. You could try to install the bromine first and then block it, um, and then you can after that, let me see if I can just draw it right there. So let's say, if I do, first step would be the BR2 with FeBr3. I'll try to kind of contain this in a small space. And then in the second step, I can do H2SO4 with the sulfuric with SO3. So just to kind of put it on the para position, because bromine is also ortho and para director, so keep that in mind. So whenever you have both positions available, typically goes on the para position because it's less hindered. And then eventually I'm going to do Friedel-Craft here. So if I try to do Friedel-Craft now, what's going to be the issue? The Friedel-Craft may not be that successful because of this strong electron withdrawing group that's going to be present on it. So maybe cannot do Friedel-Craft at this location, at this point. So that's why going this route is not going to be that beneficial. It's not going to help you to get the product you really want. Typically, there are multiple ways of doing these synthesis reactions. As long as you show the right way, the right reagents at the right time, not messing up with these limitations, you should be okay when you do these synthesis problems. If you have any questions, feel free to leave in comments in the section below.